Thanks for the opening. It's my pleasure to start the whole activity of today. What I'm going to present today is an open attestation and authentication infrastructure to trusted execution platform. My name is Zhang Yuanyuan. I'm currently working in the CS department in Shanghai Jiao University. My research interest resides at computer system security, especially trusted execution environment related topics, including remote attestation design, fuzzing methods on enclave applications and SDKs, and etc. So today we're going to bring open attestation authentication topic to all. Trusted execution environment technology is an emerging system security solution of a cloud environment has been discussed intensively for more than a decade. Thanks to the effort made by both academia and industry, TE has been popularized for IoT devices, smartphones, industrial control systems, workstations to cloud servers. There are majorly two different genres of TE technology. One is a non-enclave TE, such as ARM, Trust Zone, and the TPM. And the rest is enclave-based TE. Let's have a look. It's based on secure processor and memory encryption technology, also known as the enclave TE. So today, for example, we have Intel SGX and AMD. Both are the off-the-shelf enclave TE implementations on the most popular CPUs. For RISC-V instruction set architecture, we also have emerging TE designs such as Septum, Keystone from UC Berkeley, and Cure from Professor Seti's team. Now, recently, we're working together on something on the attestation design on Cure. And the Peng Lai is also a RISC-V system TE implementation. Okay. So far, we only have the prototypes of those designs, but they provide essential elements in implementing a next-generation open enclave system. So right now, the attestation for those systems are left blank for us to fill. So let's have a look at the TE attestation. I put a extremely simplified model on this slide. Let's have a look. In a cloud confidential computing scenario like this, and we have a tenant or a service user who want to rent a TE execution environment on the cloud provider. Before doing that, the user wants to prove the authenticity of this enclave, this TE environment. TE in response will reply with a cryptographically calculated proof, or say a token, to the user. The user seeks for a verification result from a attestation service provider, like this. And this attestation server usually has to be right now, it has to be a trusted third party or a CPU manufacturer. And they return a attestation report on the result to the tenant or the service user, and the service user will be convinced that this TEE is an authentic platform. The service is secure. So simply speaking, the entire attestation is trying to convince the tenant or service user that what you're using right now is secure. And the attestation is provided to answer their question. First is this TE authentic? And the second question is the enclave code legit? Okay. This is the highly simplified model, but the whole story is based on this logic. Let's take a little bit deeper dive into the attestation. Now we are trying to build trust for TEP users, the trusted execution platform users, just like what we mentioned before, it's the tenant or service user. But To build the trust inside this complex scenario is quite challenging because we have various stakeholders in this environment. So briefly speaking, we have at least 4 participants in this scenario. One is a chip manufacturer, platform provider, or say platform developer like SGX developer and who implement it. And the third one is the user. This is the interested party in this whole scenario who holds the question that if this platform is authentic. The fourth one is enclave authors. These participants acts like the developer of an enclave application. Okay. They all have different security requirements and claim in this whole scenario. For example, the chip manufacturer, his job is to preserve the root of secret of all the chips, because the root of security in TEE framework is this root secret is burnt inside the CPU chip. So as a chip manufacturer, it has the innate responsibility to preserve and attest the root of security. The second participant, the developer, they implement a attestation service for users. So they will provide the whole attestation workflow and the key management and the whole story for the attestation service. The third one is the user. User's question is like, is this execution platform is a TEP and how can I test it? Okay, the last one may be the authors. Their major concern is this enclave application running on the host is a legit copy of what I have published. So they want to find out those 4 questions, find out the answer to those questions. Okay, fortunately, we have a very mature off-the-shelf TE industrial implementation by Intel Corporation. It's called SGX. It's also the most intensively and thoroughly studied TEE implementation nowadays in both academia and the industry. And Intel SGX has provided a sample code on their website of how to do a local attestation and a remote attestation. And Intel also provide an SGX SDK and encourage all the developers to use this SDK to develop a remote attestation. But they also regulate how this verification should be done. As we have depicted in this slide, we can see that Intel is responsible for all the attestation services. First is the key provisioning. Intel is a chip manufacturer. They burn the keys, unique and secret provisioning, secret and seal secret, into each piece of chip. And the second one is a remote attestation service. And he's responsible to answer the challenges from a service user and enclave app developers that if this platform is a trustworthy platform. And also there is the third party is called a third attestation service, also known as enclave licensing. And maybe Intel right now has not implemented a licensing system for SGX framework, but in their SDM, software developer menu, they suggest that this thing exists. And the job of enclave licensing is to issue software license to each enclave developers. As we can see, this is the whole architecture of Intel SGX attestation. Intel SGX is supposed to be a process-based TE framework. Process-based is like they provide enclaves for applications. But right now, there is a peer implementation as a virtual machine-based TE implementation as a well-known AMD SEV remote framework. It's a secure encrypted virtualization. SEV. So their architecture is roughly like what I have depicted on this slide, but unfortunately, we have not seen any practical attestation services based on this architecture. So we have found some papers like suggesting the way how they do the attestation. Okay, SEV is a so-called a VM-based TEE framework. So the users are no longer the users are no longer like renting a TEE to execute their private code or data. They are the tenant of VM. The whole VM is running. It's kind of like the whole VM is running on the enclave. So the kernel itself is just like a system level enclave running on top of the hypervisor. So the attestation has a very different application, than in Intel SGX. The attestation is mostly like happen in two scenarios. One is when they deploy a VM. The other one is when they migrate a VM to the SE platform. So the whole attestation is like this. But also, as we can see, that AMD still play a very important role, essential role in the whole attestation service. They are issuing the keys, so they have a key server to provide the root key attestation, and also an owner certificate authority to issue the certificate for each VM. Okay, we have seen those two typical industrial implementations. Now we dive a little bit deeper into Intel remote attestation based on EPID. EPID is mostly like what we have depicted in this picture. So the whole procedure is quite straightforward. The root of secret is provisioning secret. Intel keep a copy on their own server and issue one copy on the eFuse of the CPU on the CPU die. So when the platform established, they have a way to derive a common secret with Intel based on this provisioning secret. So they can attest each other by exchanging encrypted messages through this channel. So the whole provisioning secret is based on, the first is the Intel provisioning server derives the provisioning key based on the provisioning secret and use this PK, this provisioning key, to encrypt the attestation key and send it to the platform. The attestation key is also known as a member private key based on the EPID signature scheme. So after receiving the attestation key, the platform can decrypt this part of message and get attestation key and use this attestation private key to sign the quote. Quote is the measurement and the report of this platform and send this signed quote to the challenger. Challenger is the user and the ISP who want to attest this platform. And the attestation phase is the challenger will send the received signature to a attestation server to get the report if this platform is legit or not. So we can see that the whole thing is every step we have to go to the Intel server to get attested. So this is a highly concentrated, highly centralized attestation method. Okay. So we can see that in SGX EPID method, that all those 4 participants in this attestation story, all their questions has to be answered by Intel. So there are a lot of efforts made to try to mitigate such a highly concentrated attestation. Intel itself has realized that this highly concentrated attestation service will cause like a very heavy burden to their attestation server. So Intel SGX also proposed a third-party remote attestation scheme called DCAP. DCAP is a data center attestation primitives. Okay, we will give a brief introduction on DCAP later. And then the second one is a Marble Run. Marble Run is a sub-project inside the Graphene. Graphene is previously known as Graphene SGX. This is a very famous open source project for SGX. Marble Run provide attestation service mesh. The third one is Opera. Opera is open remote attestation for Intel secure enclaves. This work is done by my colleague, Chen Guoxin. He also works in Jiao University, and we will work closely on attestation, remote attestation protocol design in the short future. And for the AMD family, AMD has also some implications in how to implement SEV remote attestation, but by far we haven't seen a very ideal one. It's like we have example later in the following slides. We can have a look at the design flow. Okay, maybe there are more industrial implementations on AMD SEV remote attestation, but I haven't heard which one is available for commercial use. If anyone knows, you can give me a heads up. Okay. For other open enclave families such as Keystone, Cure, and Penglai, right now we haven't designed any. We haven't seen any remote attestation design work has been done on those open enclave families. This is also our next step. We are going to work closely with the Professor Sethi on the Cure remote attestation. And then we have, let's have a look at the third-party attestation. As we have mentioned before, Intel has realized that highly concentrated, highly centralized attestation service is not quite proper for nowadays hybrid TP trust execution platform situation, and will cause a high burden to Intel Attestation Service. So they also recommend people who's running a cloud infrastructure to use their DCAP attestation. Is also known as ECDSA attestation. Use these names just because they use a elliptic curve digital signature algorithm in generating a certificate for each enclave within the local network environment. This method enables third-party attestation. It's right now it supports processors of Intel Xeon processor. So right now, if you are using a personal computer equipped with i5, i7 processor, maybe you are not be able to do any experiment on your own computer. So the feature of DCAP is it can provide a flexible provisioning based on ECDSA certificate, and this thing, this certification service is how to say this? The certification authority has been designated by Intel to the local servers. So Intel will no longer involve into the certification phase inside this local environment. So local network environment. The second feature of DCAP is allows for constructions of non-premise attestation services. And third one is it requires flexible launch control in supported Intel platforms. The last one is available under open source licensing model, so everyone can just try to implement their own DCAP implementations. As we can see in the following slides, We have the picture from Intel official website. It indicates the whole workflow of DCAP. First, we can see that on the internet, Intel still plays a very essential role in the whole attestation service. It will provide a local network, a data center caching service that will designate part of the certification power to the local data center caching service. So the data caching service can issue certificate based on how to say, I don't want to dig into the technical detail in this part. Based on the certificate that this caching service itself, the PCK certification IDs, it can issue certificate for the local enclaves instead of each local enclaves has to ask for attestation certificate on the internet. So the issuing and the attestation service can all be done within the local network and the local platform. So in this case, Intel just designate the power ones and leave the work for the local network server to complete. So this is the way to designate its power. There are some shortages on Intel DCAP. So as we can see on this slide, like the dark blue blocks, it means they resides on or in the same platform, local network, or same controlled environment, means those two and those two, they resides on the same platform or network. So there is a possibility to launch two types of attack or some privacy leak. For the first one, when the certificates are public to all, so the verifier, the ISV, will perform the verification by themselves. So when they receive the attestation report from the platform, they will send the report to verifier to verify it. If the verifier has published all the certificate to all, and the verification happen on the verifier, it might expose the SGX platform and enclave information and try to combine to reveal the privacy of the user, like who is using which platform to run what application. This kind of information will leak to all to the verifier. And also worth mentioning is like Intel SGX EPID attestation service is trying to use a group signature method to avoid this kind of privacy leak. Because they use EPID is like a group signature method, and they use one public key to verify a group of different private key signature. So when the verifier is verifying a signature from one entity, it will not know which exact entity is this one. It will know that this guy is from this group, but he cannot specify which one in the group. So this is how they prevent the privacy leak. DCAP cannot, seems DCAP right now cannot solve this problem so well. And the second attack is like this: the verifier and SGX platform together, they reside on the same platform. When the certificates are private to service providers, for example, the verifiers will make all those certificates private to himself to verify. And the ISV has to fully trust a third-party attestation result. So when verifying the SGX platform, they are on the same platform. There is a risk that they can launch a collision attack. So ISV will not receive the right and correct answer. They can collude and forge a attestation report back to ISV. So this is the risk of decap. As we can see in Marble Run is recently released attestation service in Graphene. So this, because Graphene is tightly coupled with Intel SGX, as we can see, that it has a very long history with SGX implementation. So Graphene is they changed the name to Graphene like a few months ago, some times ago. It's like Marble Run is a recently proposed attestation in Project Graphene. So they propose a coordinator. It says it's quite similar to DCAP actually. And they propose a Marble Run coordinator. This thing has to install it deployed in the cluster, especially on the server. And the marbles is a separated marbles is a Marble Run pre-made. This is like it includes some the enclave application software manifest, including the version, the TCP version, and a lot of other informations. And this thing has to integrate it with each application, Graphene application. Altogether, they are running on the SGX platform. So the Marble Run attestation actually is the attestation between the coordinator and the pre-made. So this is how the Marble Run is attesting this platform. It's similar to DCAP. It has some little tweak in it. And the next one is Opera. Opera is published on CCS 2019. This work is being done by my colleague Zheng Guoxing. This work is trying to separate, to try to decouple the attestation service from Intel. But after all, but Intel has hold all the, okay, let's have a look first. Okay, this is the architecture of Opera. The blue part is the Opera registration and the preparation phase. The pink part is the Opera attestation phase. As we can see, like attestation work has been done on the platform by attest-E, this enclave. And we have introduced a new Opera server here. This server runs independently from the target platform, and they have a issue E here. So issue E and the test E, they have to do a remote attestation between each other and try to prove that they are authentic Intel SGX enclave. And then Intel, okay, the whole thing is happening like this. Attest E send the QE quote to issue E to Intel Attestation Service. And when issue E has passed the attestation of attest E, and after they build a remote trust relationship, and then issue E will play as the attestation server in the middle of Intel Attestation Service and attest E. So issue E is trying to issue a GV cert. It's the GV cert to attest E. GV cert, there is a very important field inside GV cert is IAS report. IAS report actually is the report from IAS on issue E. So issue E will issue to attest E a GV cert, including his own attestation report from Intel Attestation Server. So make sure that issue E is an authentic Intel enclave. And then attestation, attest E, this enclave, on receiving this issue E, it will believe that he is interacting with a legitimate deputy of IAS to do the whole attestation And then attestation E will send the report of this enclave and the quote of the enclave to the server, to the ISE server. The ISE is trying to challenge if their enclave is running on a legit platform. So when it's received the report from attest E, it can just verify this they verify the signature from both attest E and from IAS. So in this case, the ISV will be convinced that this enclave is running on a legitimate TE platform. So this is the whole procedure of OPRA. Okay, next we have a quick look on AMD SEV remote attestation. This is from work published also on CCS 2019. It's insecure until proven updated. And this work, in this paper, I just copied this picture from this paper thanks to the author, and it's nicely made illustration. And this whole procedure including has two different scenarios applications. One is the deploy of the VM. The other is migration of the VM. So under those two different scenarios, and the hypervisor and the SEV firmware together, they are running the cloud server, they're the cloud provider, and their protocol initiated by the guest owner. And then the firmware, after receiving the challenge, will send the platform ID to the hypervisor and initiate all the remote attestation. And the hypervisor will send the certificate of the platform and to the customer, to the guest owner. Guest owner will be the one who go to the AMD key server to prove that this the report is cryptographically correct from SEV firmware. And if they pass the verification, and they will negotiate a transport key to continue with the following encrypted communication. The same for the migration is like the migration is slightly different from deploy. Migration is a hypervisor is trying to get a proof from the key server, and the hypervisor has to prove itself. And then after the verification, they'll forward the ARK, ASK, those chained verification result back to the guest. And then they negotiate a transport key to encrypt the following communication. This is the key establishment procedure of AMD SEV remote attestation. Okay. In their paper, they also propose two very lethal attacks for SEV. The SEV, the first one is a fake SEV. The goal is to fake the presence of SEV and gains access to guest data. The attacker can be a cloud provider. It has access to an SEV-enabled system for one-time extraction of the CK private key and the corresponding platform ID. The other one is a migration attack. Migration attack is the presumption condition is also very how to say, it's a very tight to say that, because as we can see that the CK is called the chip endorsement key. It's the key burnt by the chip manufacturer inside the die, CPU die. So it's very difficult to get a CK because cryptographically it's very, very difficult. So this assumption to me is a little bit too not very practical in the real world attack. But the author of the paper claimed that if they can have any CK private key and the platform ID or access to the management interface, so they can forge a fake SEV-enabled destination host to fool the victim to migrate their VM from a SEV to a fake SEV enabled host. So this is the attacks they have proposed in this work. Okay, let's make a quick comparison of all those implementations. As we can see, the Intel EPID and DCAP, this is like, they are focusing on the enclave remote attestation. Okay, and EPID, the pros of EPID is they provide the privacy-preserving features, and the cons is Intel is too centralized in this attestation procedure. Intel DCAP is like designate the attestation power to the third party, to the local network server, but it has the risk to be attacked by collusion attack. And somehow it's still relying on the Intel authorizing PCE. So the third one is a Marble Run. Marble Run is very close to DCAP. So it has almost we can consider that Marble Run is similar to DCAP and EPID's like a better implementation, or they provide a middle level SDK for the developers to implement their own attestation service. This is their advantage. Okay. The third one is
Just
Opera.
a minute. 5 minutes left.
Sorry.
5 minutes left for your talk. Thank you.
Oh, I'm sorry. I kind of. Okay. Thank you for the reminder. Okay. The Opera is for the third party Intel EPID, but it's highly relying on Intel EPID method. So SEV right now is he has a pros to introduce owner certificate how to say that authority, that is has exposed the risk to fake attack and migration attack. So for the attestation for the OpenTTP is like a hybrid trusted execution platform. In future, I mean, in future, for example, the next generation RISC-V platform is popularized. When it's get popular, we have a different middleware, system middleware like SGXACV, Cure, Keystone, and so on. And at that time, we are trying, are we going to have unified attestation authentication interface to provide a unified interface for the developers to develop their own attestation service? And under this assumption, we have some requirements for open attestation authentication infrastructure. First is the separation of powers. The powers should be separated from the chip manufacturers, the platform designers and implementation, and the applications and users. So, and we also require privacy preserving features for those attestation service. And the third one is a distribution of authority. That even if we separate those powers, but we in future we believe that there are more CPU manufacturers. Each one is holding the root of secret of their own brand. But how can we make attestation service not only depend on the CPU manufacturers? This is a distribution of authority. The third one is usability, and we suggest to have a unified attestation interface. And the performance is an attestation for enclave container swap. It's like, for example, if we want to have like 1,000 containers spread on controlled by Kubernetes kind of like thing on the thousands of servers, how can we make attestation fast and efficient in a short time? So we have attestation service architecture for OpenTEP at a glance. And we hope to have a fully decentralized design, but I think this is not quite practical at right now. So in our design, we can see that CPU manufacturers and still have to answer to a certificate authority, and the certificate authority can like issue the attestation key certificate onto each TP cloud. And each GP cloud has a provisioning enclave to like do the attestation service for the enclave and the VM on its own in its own local network or cloud environment. And we have ISV and tenants. They have their own like attestation request on the enclave, the legit on the enclave and the VM. And let's have a look at the secret provisioning step. We can see that the first is like the local environment, the local VM and enclave can generate the attestation key and its public key and then ask for PE to have their certification key. And if this thing can happen inside, if the tenant does not believe that this PE is authentic, and it can go to a certificate authority to ask for verification. And for the enclave remote attestation, we have what we have to pay attention is the measurement of each enclave. And we give an example of SGS quote enclave, what they provide in the measurement, that we can see that we think those features are very important to be included in the token as the token to be integrated in the attestation service is including the memory layout hash, the TCP SV and the version, and the ISV product ID and SVN, and some user choice of report data, and the epoch, the time of encryption generation, and the token generators of version, and the service provider's information is included. So the tenant, like for the VM users, is similar to the enclave actually, because we have implement prototype on Cure. Cure is the next generation Cure. The next version Cure is mostly VM-based TE architecture. So the tenant attestations is similar, and we use a similar way to measure the VM, but we haven't designed the attestation service for the application running inside the VM. This is our next step future work. And the last one is the enclave authorship authentication. This is a small part of the story, so I don't want to spend too much time since I'm already late. And for the implementation of this design, and we hope, like right now, as we most popular OpenTM ecosystem is built on the SGX like programming paradigm. Paradigm is TE hardware, kernel layer, and enclave abstract. So we for the developers, we have to develop the enclave application from scratch. We have to fight with the low-level TCP. So this is quite challenging for the lexicode and for the programmers. So next generation, we hope to have an OpenTPE programming paradigm is on top of the kernel level, we have open enclave abstract, and on top of it, we have high-level unified interface for developers. So right now, we have some options to have some options like open enclave, gramming, edgeless RT, and so on. On top of this, we can easier for us to implement the attestation service, because we recommend to provide some attestation like service workflow, or standardize the attestation workflow and the protocol format, message format, and the cipher suite we use. So on top of this, attestation can be easier to implement. Okay, here's the conclusion of my future work. The conclusion part is the trust from open hybrid TEP is built on the attestation service. No trust. There's no the trust is the trust we have to build is in between cloud server user and cloud provider, and developer and cloud provider. Mostly it's convincing that people can use this cloud secret confidential computing service more confidentially. The second one is authentication service should be open and decentralized, like verifying authenticity of a chip and issuing attestation certificate, and authorship authentication should be separated to different parties. And right now we have emerging work, as we have depicted in the slide. We have Opera, programming, and these are very promising implementations of attestation service, but they are based on SGX, and most of them are like within this framework. So for the next generation open enclave ecosystem, we have to jump out of the frame and have a more open and unified attestation and authentication interface provide for the high-level users. Right now, we have IETF REDS interest group is working on attestation, but they are not only focusing on TEE attestation. So there are more work to do. And the future work is our implementation on CURE. Right now, we are in work very tightly with Professor Setti's group. Attempt to unify the remote attestation is our next step. Standardize the attestation flow and the protocol formatting. And the last one is attend to a new attestation paradigms. For example, if we have a container swamp attestation, what can we do to make it more efficient? And in the end, I want to say that decentralized is a very good goal to aim in our research. But right now, we are trying to find ways to introduce like a blockchain or like a multi-party computing, try to use those skill technologies to remove the centralized CA or other third-party authorities. I hope we can find more new ways to solve this. Thank you, everyone.
Okay, thank you, Yuanyuan, for an interesting overview and also a vision for the near future and long-term future, so to say. Now, is there any question for Yuanyuan? We have some. We can. It's a workshop. We would like to take some time for the question.
Hi, this is Silvio from Huawei. I would like to ask a question. First, I would like to say thanks for the great overview, and I think it's quite comprehensive. And I'm really glad to see that your group will be working on the CURE attestation. I guess the only comment I would make is that I haven't seen much about the revocation of attestation keys in case one platform, would have a problem. And I guess that's going to be important to consider in these designs, especially because all these attestation architecture, they rely on firmware, firmware may have bugs. So that would be something also interesting to know if you would consider that's a job for the enclave or for the CPU vendors, or rather it's something that should be handled with the framework.
Okay, a revocation list is usually, it's like for example, in SGX will be sent at a provisioning, or a secret provisioning phase. It will send to the applicants that to tell him that the one you're using is revocated or not. So this will be a very natural part of the design, will be integrated into our next step. So I don't know if I have answered this like technical.
It will
be, yeah.
Yeah, I guess that's a good start. Probably, after revocation needs to come also some way to recover eventually. So that's what I think we should consider in the future for these enhancements. But thank you.
So, just one comment is that indeed this work and this also joint work with Yuanyuan shows that there is no universal solution because, of course, Intel has its own proposal with group signatures, but decentralization will be an important point in very, I mean, whenever we have more and more TEEs used in different contexts, there will be two questions, I think. One is this decentralization, or at least less trust in manufacturer, and we still see that the existing solutions are still very much use this kind of, they have still a lot of confidence in manufacturer, assumed a lot of context in manufacturer. And another thing is, as Yuanyuan said, this interface that unifies different solutions, because we can't say we will have only one solution and everything must be complying to that solution. This is why we are doing this research. So anybody else has a question to this, I think, very important matter in the within this trusted execution environment, because the matter of trust and how you provision it is the very fundamental. Any other? Okay, I see all these names. You can pick someone. Okay. So if there is no other question, then I would like to thank Yuanyuan for her time, and of course she opens our workshop, which is on building trustworthy systems, and distributing trust is one of the most important aspects. And I think using blockchain or secure multi-party computation would be interesting. However, I am not sure about its practicality and pragmatism that we need sometimes in real world. But of course, are very important points for and directions for research. Thanks a lot.